Hi y'all. I wanted to give you a quick one, a quick little video here on shear moment diagrams again. This looks like an easy one, doesn't it? But I want to talk to you about what goes on here. This is something special and require a little bit of thinking here. Okay. We're talking about shear moment diagram again. Shear force we represent with a V, bending moment with an M, and look at my last video. And you can see a better explanation of this. The last video you used the graphic method to do this, but this one we're not going to be able to employ the graphic method. We're going to have to use the equation method. Okay, so we're going to solve this in a little bit different way. And then you remember we had the order of the lines. And this is something that I made up, so you won't see this anywhere else, but well, maybe you will. But this is kind of like we talked about these graphs, and we have different graphs. We have here we have the shear graph and the moment graph. Okay, shear moment. That's where those diagrams. So I do these all in order always because this graph is related to this graph is related to that graph, and they're related if you remember by. This graph is the integral of that graph. This graph is the integral of that graph. So if you take the integrals, this is what those line shapes are going to look like. It'll look like a straight line. This will be like y equals 5. This will be like y equals 5x. This will be like 5x squared. This is 5x cubed. And so if you remember the order of the lines here, it makes it a little bit easier to plot. And so one of the things that you, on this problem, well, on all these problems, the very first thing you need to do is what? Find global equilibrium. Here we go. Okay. So let's just call this, we'll call this over here A, and we'll call this B. Okay, so I have over here a BY, just a roller, and then over here I have an AY, a pin connection, and I also have, let's call it AX. But AX, there are no X forces anywhere on this beam. I have a distributed load, but they're all in the Y direction, so AX is 0. Okay. He's there if I need him, but just not for this loading scenario. Okay. So what I tell you here is that this is 10 kilonewtons per meter at the tallest point over here. So what is it at the shortest point over there? Well, it's just 0. Well, what would it be in the middle? About 5. So remember our load backpack. As I walk along that beam, every step I take, I'm getting a little bit of load, but it's not linear like it was before when we had just a flat line across there. Okay, so I'm getting it at not a linear rate. I'm acquiring load at a parabolic rate. Okay, and again, let's look at our order of the lines. We have on our load curve we have this. So our V curve is going to be that, and our M curve is going to be a cubic, right? This is an x squared. This is an x cubed down here. This is just a plain old x. Okay, so we're starting off with that here. So let's see if we can plot this. Okay. So the very first thing I want to do, let me put my discontinuity in there. I just have one at the very end of the beam, is find global equilibrium. Okay, so global equilibrium. Not writing very good today. Okay, so global equilibrium means just find out what's going on where this is hooked to the world here. All right. And so what I'm going to do is I know that I want to change this distributed load into a concentrated force. I'll make it blue, okay? So the concentrated force is here. And how do I find that? Well, I just find the area of this shape here. And it's not really an area, but what happens when I multiply 10 kilonewtons per meter times 9 meters of it, right? The meters cancel out. I'm left with just plain kilonewtons, which is the load. Okay, now this is a triangle, so it's going to be 1/2 the base times the height, and my meters are going to cancel out and leave me with 45 kilonewtons, okay? Now I'll need that number to calculate my global equilibrium here. So let's just take the sum of the moments at point A, okay? So summing the moments at point A, now where does this go? You remember? It's the centroid for a right triangle. And remember, the centroid for a triangle is a third of the base, but that's on the fat end of the triangle. So that would be a third of this, which would make this distance here 2/3, and 2/3 of 9 is 6 meters, okay? So let's just call that 6 meters from there over to there, okay? So the sum of the moments about A equals 0 equals, let's call it, remember, here's our, to remind us that that's the positive direction, negative 45 times 6, we should be getting good at this by now, plus by times 9, okay? So by equals, let's see, the 9 will go into the 45 5 times 6 is 30 kilonewtons, okay? So by is 30 kilonewtons, and the sum of the forces in the y tells me I got a 45 going down and a 30 going up, so AY has to be how big? 15, okay? There you go. All right, so we've got our global equilibrium knocked out. I can go ahead and erase this out of the way. Okay, here we go. Where did my black marker go? There it is. Okay. So let's do this. So here we go. Remember how to plot this just like we did before, okay? We got our load back on. We're going to step onto our beam. The first thing we're going to encounter is the 15. It's going to make me go up 15. There we are. And over this total amount of load here, I'm going to gather up 45 kilonewtons, aren't I? So if I start off at 15, I'm going to go down 45, which would take me to negative 30, right? So for 15, there's the 30 more, that's the 45, isn't it? But how do I get from there to there, okay? Remember we talked about last time, we talked about accumulating load. We're accumulating it fast and slow or slow then fast. Well, in this case, right, if I take a step over here, I'm just getting a little bit of load. But if I take a step over here, I'm getting a lot of load. So this is definitely a slow then fast, okay? And then slow, think about skiing. Slow is bunny slope, that's flat. And then fast is black diamond. There we go at the end, right? Okay, so here's what my shear diagram looks like. Oh, then I've got the 30 over here at the end that takes me back home again, don't I? Okay, so the question about this is, you know, if you're going to use the graphic method, you would just look at that shape and look at that shape and you just find those shaped areas and then plot your M. But you can't do that here, okay? So what are we going to do? How do we find X? Well, it's a little bit different because this looks semi-parabolic, doesn't it? But it's not semi-parabolic. Don't be fooled. Admiral Akbar would say, it's a trap. Okay, that's silly. All right, so this one over here, here's the vertex here, okay? So this is just like the slice, like if I had like a parabolic shape, we're talking about just a slice off the side of it here, right? There's the vertex over here. So I can't use those tables in the back of the book. So I've got to find X. So what are we going to do? Well, here's what we're going to do. We're going to cut this beam in half right here. Okay? Now, how many of you think that X, well, duh, it's 6. Because Henson's drawings are always to scale. Probably not. Okay, don't fall for that trick. I have never found one yet where that intersection happens at the centroid of a triangle. I haven't found one yet. There may be a magic triangle out there, but I haven't found it. Okay, it's a trick. So let's find X. So let's just take this line and let's cut this in half. Now you remember what happens on our M diagram down here? Whenever we go, we have positive area. Whoa, that's not very good. Positive area, positive slope. Negative area, negative slope. So our M diagram is going to have a positive slope and then a negative slope. What's it going to look like? It's going to go like this. Fast, slow. So it's going to go like this. Okay. And then slow, fast. Okay, so that's what my graph is going to look like. But the question is, what's the value of M at that point right there? We'll call it a question mark. Okay. And that's what we're trying to find. So in order to do that, we need to find this distance X right here. So let's take our original diagram and let's just chop this thing in half right there, okay? Oh, let me not draw that on there. So I have over here, I have a 15, and then I have this. Okay? let's see, now how big is this? How tall is that? Well, it's not 10 because I cut it over here. And I cut it at a distance x, didn't I? I don't even know where that is. Okay? If only we had an equation that would tell us like these y values at any point on the beam. Wait, there is one. And it goes like this. Y equals mx plus b. Okay? And so b, let's call that the y-intercept. It's 0. So what's the slope? The slope is the rise over the run, or 10 over 9. So 10 over 9x equals y. Okay, so if I ask you, like, what's the height at 2 meters? Well, you just plug a 2 in there, wouldn't you? And you tell me what the height was. So what happens if I ask you, what's the height at x meters? Well, that is the height at x meters right there. So this height over here is 10 ninths x. Now, what happens when I cut the beams? I tell my students this is silly, y'all, but you won't forget it. Here we go. You ready? You have to do this in a Mickey Mouse voice. Every time you cut the beam, you must have a M in V. Okay, so we have, here's your N, here's your V, and here's your M. But you have to say it in a Mickey Mouse voice, okay? So there's my M and V where I cut the beam. Those are those internal forces that are going on, okay? So you tell me, how can I write an equation that would give me V? What equation would give me V? Oh, I don't know. Maybe the sum of the forces in the y would do it, wouldn't it? Okay. Again, we got to turn this into a concentrated load. How big is that load? It's 1/2 the base, which is x, right? This is x, times the height, which is 10 ninths x. And so let's see. In the y direction, I have minus v, and then I have minus, or let's go plus 15, and then minus, what is that? 5 ninths x squared. Okay, so v equals 15 minus 5 ninths x squared, right? And then can I write an equation for m, and maybe I can get this point here. So how about sum of the moments? I'll just call it at x, at a distance x. So all the m and the v and the n are knocked out. So, but you never knock out moments, do you? So I've drawn that counterclockwise, which is positive. So there's m, and then I've got this is going well, clockwise. So minus 15 times x, and then this is going counterclockwise. So that's going to be positive. So that's going to be plus 5 ninths x squared, which is how big this is, right? 5 ninths x squared, times the distance, which is 1/3 of the base, right? Times x over 3. So m equals, let's see, what does that turn into? 3 times 9 is 27, x cubed minus 15x, okay? And so here we go. How do I solve this? So I have an equation for m, and I have an equation for v. Well, you know what? What is v here? At a distance x, v is 0, isn't it? So 0 equals 15 minus 5 ninths x squared. So if I solve that, x, what's that x going to be equal to? Let's see. My handy dandy calculator here. Let's see. 15 times 9 equals, divided by 5 equals 27, and the square root of that is 3 root 3, which is equal to 5.196 or 5.2. So x equals 5.2 meters. So x here is 5.2 meters. Well, guess what? That's where the maximum moment occurs, isn't it? That's what I'm interested in. So what happens if I put right there a 5.2 and right there I put a 5.2? Let's see what we get there. 5.2, oh, I don't know how to use this calculator very good. There we go, got my better calculator. Clear. 5.2 cubed times 5 divided by 27 equals 26.03 minus 15 times 5.2 equals 51.96. Is that right? Let me do that one more time. Let's see. 5 times 5.2 cubed equals, divided by 27 equals, minus 15 times 5.2. Yep, 51 point, let's call it 52, right? Okay, so this is going to equal over here 52 kilonewton meters. Okay, the units here are kilonewtons on this graph, and on this graph the units are kilonewton meters. Okay, and that is how you solve for these numbers using the equation method.